Okay, now it's recording? Yeah. So, this course, again, I remind you, the plan is to talk about lattices and random groups. We start by reviewing the theory of lattices, then we will generalize it to, can think of a lattice as a random subgroup. This brings us to the definition of invariant random subgroups. Then I will spend the second third of the course talking about invariant random subgroup, and then I will move to non-invariant random subgroup. So meanwhile, we're talking about lattices, and you asked me for literature. So there is no good literature book for the full course. Actually, I will switch every 2 weeks. Now I'm following this note, which is a lecture note from a course that I gave in 2012, but it's an archive from 2015, and it's called Lecture on Lattices and Locally Symmetric Spaces. And actually, I follow only the first lecture there. So what I did last time and what I'll do today is contained in the first lecture. I think then I will move to other stuff. You asked me what I'm following. So now I'm following this. It's called Lecture on Lattices and Locally Symmetric Spaces by some guy named Tsachik Gelander from 2014 on the archive. I follow the first lecture here out of 4. In Utah, I gave 4 talks of 1 hour. I remember even Ian Egol remarked about the speed that the amount of stuff that I put in every talk. But then when I wrote it, I put details, so it looks like more material than you can do before talks. After I'll follow the first talk here, I think I'll start to describe Weizmann theorem, and I will follow Margulis proof, which is beautiful and not very well known, I think, proof for the Weizmann theorem. And then we move on to other stuff. So we were discussing examples of lattices. We gave several examples. I'll give more. Oh, there was an issue about unimodularity. Somehow people complained that the argument I gave you was not consistent. I think it can be made consistent by switching steps there, okay, we view lattices.
Okay, statement.
There are two ways we're viewing lattices. So one way is we say that H in G is cofinite. So G is a locally compact always. If G mod H admits G invariant probability measure. And, so that's the definition of cofinite, and a lattice is a cofinite discrete subgroup. Now, the tree is not very fixed.
No, it has television.
Yeah, there's something relevant. No,
but then you won't be able to see the ball.
I don't mind.
the ball.
No, but
Yes.
Okay.
Now, this was one definition of a lattice, and the other a lattice is a discrete subgroup admitting a finite volume fundamental number. with respect to the Haar measure. So you have a fundamental domain with finite Haar measure. And I use this definition to show you that one exercise was to prove the equivalent. And I use this definition to show that the lattices, if G admit a lattice, then it's unimodular. And then was the issue whether I use left Haar measure or right Haar measure. You can easily make it work, or maybe not easily, but you can make it work. Another way is to consider this way, and to think of this fact that G mod H carries a invariant measure implies, so if gamma is a lattice, if H is finite, then we know that the modular character of G restricted to H coincide with the modular character of H. So in particular, if H is discrete, this implies that, or if H is unimodular in general, discrete group is unimodular. Unimodular means that the left Haar measure is right Haar invariant, so it means that, in other words, that the modular character is the trivial character. So if H is unimodular, it means that that H is contained in the kernel of the modular character. So the character delta G, which is a map from G to the real, a multiplicative homomorphism, factors to G mod gamma. You can factor to the map from G mod gamma if gamma is a lattice. Okay, if H is let's say if H is unimodular, factors to G mod H in that case. So so the image, okay, so let's still be noted by big G if you want to be bound from G mod H to R star, and then you can push the probability measure from here to a probability measure on R. Whenever you have a nice map, a continuous map, modular character is continuous because we speak only about Borel regular measure, and but also, and whenever you have a measurable map, you can push measure from the domain to the target, and this induces a G invariant probability measure on R star. So the measure must be inside R, because it's the character, the measure will be so the measure will be invariant under the image of so the image is a group, a subgroup of R with finite measure. With probability measure is compact. Or if you want inside R, you don't have subgroup of finite measure except the trivial group, implies that it's a trivial. So that's another proof that lattices are, if G admit lattices, then it's unimodular. And if you look at the notes that Tal made, there are like three alternative proofs for this. So not every group admit a lattice because we know that not every group is unimodular. We gave the example of the affine group of the line. Group A to speak is not unimodular, so it doesn't have lattices. Usually, solvable group tends to not admit lattices. It's not a true statement. There are many solvable groups that admit lattices, but a generic solvable group does not admit lattices. But also, I gave you an exercise to show that the nilpotent groups are always unimodular, right? Using the central series to show that the modular character is trivial for the nilpotent group, and therefore every nilpotent group is unimodular, unlike solvable group. But still, there are examples of nilpotent groups, with nilpotent Lie groups even, like unipotent groups, which do not admit lattices. So it's not an if and only if condition. There are many groups which are unimodular but do not admit lattices. Last time we spoke about yes.
The end of the proof. The image is a subgroup of R. That's the image of delta G, the image of H, or the image of which map of delta G?
Of delta G. The image delta G is a character. So the image of a character is always the image of a character is always a subgroup. H is in the kernel. So you get the image is a subgroup of R, and on this subgroup we have the measure that we push from G mod H, the probability measure, which must be the R measure of the image. And so it's a subgroup of finite R measure. It's a compact subgroup of R.
Okay.
Is good. So
connectedness. Any Q stars, which is your separated.
Sorry?
To require connectedness.
No, it doesn't require connectedness, this argument. No. So this argument is G, it's only a locally compact. It doesn't need to be. So I spoke about the important groups. So actually there are many important groups which admit lattices, and there is a beautiful relatively elementary theory, but with extremely nice of Malchev describing the theory of lattices in the important group. Anyhow, one example is take the Heisenberg group. H is a unipotent three-dimensional group, A, B, and C are R. So that's a group. And inside you take gamma, or let's call it G. Inside you take gamma, which looks the same. One, A, B, one. Okay, let's put alpha, beta, gamma. And alpha, beta, and gamma are in Z integer. So that's an example of a lattice. Actually, it's an example of what is called arithmetic lattice, which I will define later. And this lattice, you can show, I gave you an exercise, that's example, but also an exercise to show that gamma is a co-compact lattice. You actually find a fundamental domain, which is the unit cube here. So it will be a fundamental domain. So it's a co-compact lattice. If you have a discrete group which is co-compact, it's always a lattice. There are lattices which are not co-compact. There are co-compact subgroups which are not co-finite. But if you're both discrete and co-compact, then the fundamental domain is finite measure. So we will have
What example is there? We link to them too?
Yeah. So for this, I will refer you to Raghunathan. It's a good question. It's not trivial to find such example. I think the example, constructor is a 10-dimensional Lie group.
Or on?
Yeah, it's a really group. The point is that, okay, somehow there's a beautiful theory of lattices. Many of you knows part of it about rigidity and arithmeticity and so on. Somehow this all started by studying nilpotent groups, and you can see many sides of this theory for nilpotent group. And it turned out that in nilpotent group, a lattice is always arithmetic in itself. If you have a nilpotent Lie group and you have a lattice, then there is a rational structure on G such that the lattice is a subgroup of finite index inside G of Z, like in this example. This will imply that the Lie group, the Lie algebra, is the coefficient of the Lie algebra. There is the structural coefficient of the Lie algebra. The structural constants of the Lie algebra. So you take a base and you write the commutator and blah blah blah. So that gives you a structural constant. This implies that you can find a base such that the structural constants are rational. And then what Raghunathan is doing in his book, he has a chapter about lattices in nilpotent group, and then he just give he show by dimension arguments. So he consider all nilpotent Lie group of a certain type. I mean, some semi-direct product of blah blah and something, and then he showed that this group is like this space has a positive dimension, but inside it the only smaller dimension subspace meets rational. So with some argument like that, he construct a lattice, a group such that such a coefficient structure coefficient are not rational, and therefore it's an important Lie group without a lattice, although it can be presented as a unipotent subgroup. So that's I recommend you to read this chapter in Raghunathan, although I will probably not. Sometimes in the past I gave courses about lattices, and then I spent several lectures describing the theory of nilpotent group because it's a beautiful theory. I think this time I want to be quicker about lattices and move to one. Anyhow, this theory of culture is really nice. Maybe you can speak about it in the midrasha. So that's an example of a group with a lattice, the Heisenberg group. Another example now is about totally disconnected, but also important example. So let T, K be a tree, K regular tree. So this is an infinite tree, there are no leaves. It's K regular, so let's say if K is 3, just you start to draw it, and at some point you have to stop, although in your imagination it continues to infinity. So it's an infinite tree, non-rooted, like there's no special vertex, and let G be the group of automorphism of T. So this is a very nice example of a locally compact group, which is totally disconnected. So I should tell you what is the topology on this group. So the topology is the most natural topology you can imagine. So this group acts on the tree. When you define a topology on a group, all you need to say is what does it mean to be close to the identity. So the topology is invariant, you can move it to any other point. So here to be close to the identity means to act trivially on a large subgroup. so if you want a base of identity neighborhood, consisting of the pointwise stabilizer of, let's say, G R X naught, which is the group of all G in G, such that G restricted to the ball of radius R around X naught. I never know if you write first the point or the radius. No, no problem. So R is the radius. So X naught is a fixed point, and R varies is the identity. Identity. And here I take a R equals okay, this is GXR and well, X naught is fixed and R belongs to the. So if you want to fix this point, X naught, so I said the tree is not rooted, but for describing a base of identity neighborhood, you can fix one point and then look at a large ball around this point. And then look at the set of all elements that fix all vertices here pointwise. And then here outside this ball, they start to act interesting. So in fact, and then it's not hard to check that this is indeed a topological group, and this subgroup is this is actually a subgroup. GR X naught is a compact but also open subgroup. So you see in this example that G actually admits a base of identity neighborhood consisting of open compact subgroups. And this is not a lack, it's always the case. Whenever you have a totally disconnected locally compact group, that's a theorem, it's called the Van Dantzig lemma, I think, but it's not hard to prove, but it's a beautiful and extremely useful theorem. So that's a part of a general statement. In fact, maybe I'll write it for you. In fact, this is a general. This is a general phenomenon. So this is a totally disconnected locally compact group. No, it's like the opposite of legal. In fact, this is a general phenomenon that you have a base of identity neighborhood which consists of open compact subgroups. So this is called Van Dantzig. C. What?
I think it's Z.
IG. Van Dantzig lemma. But I'll call it a theorem because it's something that everyone should know, and it's hard to prove. You can do it as a star exercise, or if you want, I can tell you the proof. But the lemma says that if G is totally disconnected then G admits a base of identity neighborhood consisting of open compact subgroups. That's the important part of that. It means subgroups. Every locally compact space means a base of open sets with compact closure. If it's total, open compact. Once you have an open subgroup, by the way, is always closed. That's so the fact that these are open in every neighborhood, you can find a subgroup, an open subgroup. So it's a good thing to know.
It doesn't imply that like this is the only example. Like,
No. There are many examples of totally disconnected group. There is a beautiful theory that is currently investigated by people like George Willis and Pierre-Emmanuel Capras, and it's a very rich theory. In fact, if you already asked, the domain of locally compact groups, in a sense, splits to the study of Lie groups and the study of totally disconnected. And the reason for that starts with the Hilbert fifth problem. So Hilbert fifth problem is one of the famous. There was this lecture of Hilbert, where he gave 23 problems, and some of them are still open, like the Stokes equation or the Riemann hypothesis, and others, but some of them were solved quickly, and some of them solved but not quickly. There was actually a large activity which brought to the solution, and this example of that is the Hilbert fifth problem. I think the solution should get reviewed to Montgomery, Zipping, Yameva, Gleason, and probably some others. There are several books about it, in particular the books by Montgomery, Zipping. The theorem says that if you have there are several ways to state the theorem. One of them that if you have a locally compact group, which is also a manifold, topologically, then it's a Lie group. It means a smooth structure and an analytic structure. Another way to state it is that a group with no small subgroups is a Lie group. If you have a locally compact group without small subgroups, then it's a Lie group. Here you have small subgroup. What does it mean, small subgroup? In every identity neighborhood, you can find a non-trivial subgroup. So if you have a locally compact group, you immediately can see whether it's a Lie group or not. More than that, every locally compact group, you can look at a connected component of identity. I'm diversing by orthogonality to what I plan to talk, but it's no one complain, I will continue a bit. So if you start with a locally compact group, the connected component of identity is also a locally compact subgroup, the closed subgroup, and it's a connected group. So part of the theory of this Montgomery, Zipping, Gleason, actually this I think would be Gleason theorem. I shouldn't say name because I probably make mistakes, but it says that every connected locally compact group is an inverse limit of Lie groups. It means that inside in every open subset or open identity neighborhood, you can find a small compact subgroup, such that which is normal, and the quotient by this subgroup is a Lie group, the final dimension. So this gives a very good description of connected locally compact group. So this, because we understand very well Lie groups, there is this Lie theory developed by many people. And we know in a sense precisely what are all possible Lie groups in some sense. We have understand solvable Lie group, you understand semi-simple Lie group, you have the Levy decomposition, there are so many structural theorems. And now with this theorem of Gleason, Yameba, I don't know, it helps us to understand every connected locally compact group. Every such group is the inverse limit of Lie. So this leaves us to study the quotient by the connected group. And the quotient by the connected component is the totally disconnected. It's always a locally compact, totally disconnected group, like this group, the group of a domophysium of a tree. It could be a group of domophysium of another graph. It could be, there are various examples, and there is a beautiful theory about it. But I will not, and there are also some statements about relating, if you understand locally compact, if you understand totally, once you want to prove a theorem for a locally compact group. And so you try it for Lie groups. You succeed, you try it for inverse limits, then you know you have it for connected. Then you try to prove it for totally disconnected group. And if you succeed in both mission, then you will probably know to do it for the combination. So there's some theory how to connect the totally disconnected quotient with the connected. So that's how we work. That's how people in locally disconnect in locally compact group work. So most of the current work is about totally disconnected. And also these totally disconnected groups are they're not out of the blue. They're related, like Lie groups we like because they're related to symmetric spaces and Riemannian geometry and so on. Also, this totally disconnected group, many of them are linear groups over locally compact field, like p-adic field, and they're related to what's called what it's building and so on. In particular, this become a bit advanced, but if you take here K to be prime plus 1, then this tree will be what it's building of the group SL2QP, if it's M-1 is prime. And G, okay. G is some group which contains SL2 over the field, the compact sum. Okay, that's going too far. I think, anyhow, the starting, maybe the most important basic result about totally disconnected local compact group is this Van Dantzig theorem, which you should be familiar. And if you ask me, I can give a proof, but maybe next time. If someone asks, I will give a proof, but next time because I need to think of before.
If another component is co-compact, that means the group is still an inverse limit of the group.
Sorry?
If the connected component is co-compact, that means the group is
If yeah. Okay. So now we're going back to this tree, and I want to, I described you this locally compact group, but I also want to give you a lattice in this. So there are plenty of lattices there. There is a theory about lattices in trees. A beautiful theory like somehow simulates lattices in Lie group, but also has other characteristics. So what is the most basic example there? Is the following. So pick K colors and color the tree with these K colors. For instance, pick K coloring.
Same thing, run.
Just a minute. Of TK. TK is a K regular tree. And then I just suppose in this picture, so it was 3 regular trees. So I color it with 3 colors. I go maybe 1, 2, 3, and then I move here. So it's 2, 3. The edges, yeah. Pick K legal edge coloring of TK. So actually you can define some law here how to do it. Like I always but anyhow it's an easy exercise to see that You can always do that to infinity. So you just pick a colorway, and then let gamma, set gamma to be the group of all G in G, all gamma in G, that preserve okay, and so that's a so an exercise for you. Is that gamma is discrete and proper. So, in fact, it's not hard. In fact, gamma act what is called simply transitively on the vertices of the tree. For any two vertices, there is a unique element that refers to that. So fundamental domain for gamma will be this compact group G1 X. Anyhow, so that's an example of a tree lattices. Lattice. There are also plenty of non-uniform lattices in this G, and yeah. Okay. If you have no question, I will move to my last example before going through some basic properties of lattices. So another example, which is, in my opinion, like a more important reason to study lattices, comes from geometry. So we saw example coming from number theory. We saw example coming from combinatorics. Now for geometry. So here is the last example I want to describe. Again, I will say words that maybe will be new for some of you. So let sigma be a compact surface of genus. So it's what we draw like that usually. And so by the way, I think Tomer asked me, so I'll answer everyone. So what is the material? So currently this is the material, but it will change and I will update, but also how to get credit. And the way to get credit is to answer some of the problems that I give. If you answer enough problems, you don't need to answer all of them, but if you answer enough, then you will get this 90. If you answer 20, you will get 100. So and anything in between. Yeah. So yeah, so I give many problems. You write a solution, and at one point you send it either to me or to if you want if I can get a grader, then a grader. And see. So let's see what be a compact surface of genus 2. So it is known that such a surface admits a hyperbolic structure, which means there is a Riemannian, you can associate a Riemannian metric here. Again, for some of you, this may be You don't know that. You don't know, but I just say so you can associate a Riemannian metric of curvature, constant curvature minus one. So and actually there are plenty of ways to do that. That is what we call the Teichmüller theorem, which says that there is a like positive dimensional space of hyperbolic metrics on the surface. So pick and hyperbolic metric on sigma. So somehow it's a metric here that every point looks like a saddle. There is a -1 curvature, sectional curvature. And and then the fundamental group, I take gamma to be the fundamental group of this surface. So by the way, this is a group that we can algebraically understand very well. We can write a presentation of the fundamental group if you call this loop A1 and this loop B1, and similarly we have A2 and B2. So that's the generators for the fundamental group. So gamma as a presentation is generated by these four elements and one relation. So the relation is that A1 B1 times A2 B2 equals the identity. So it's a one relator. And actually every surface, every closed surface is a one relator group. So it's defined by two G generators and one relation which is the product of them. So that's an example of one relator group. So algebraically we understand it quite well. But now since I gave it an hyperbolic metric, you have, by covering theory, the group of deck transformation, the holonomy of this, will give you an embedding. Gamma embeds in the group of isometries of the universal cover. Well, sigma is the universal cover. Now, if you pull the hyperbolic metric from the surface to the universal cover, you will get that this just the hyperbolic plane. What is the hyperbolic plane? Some of you know several models. They're all equivalent. One of them is the upper half space model. It's a set of all x and y inside R, such that y is positive, and the distance, you measure distances, is like the Euclidean distance, except you divide by the altitude. So if you want, and then that's a model for the hyperbolic space. It's in a sense much natural geometry than the Euclidean geometry for some reason. And the group of all isometries of that space, gamma embeds there, and the quotient of H2 modulo this image of gamma will give you exactly the lattice. But this group is also known to be a group of 2 by 2 matrices with determinant 1. We know that matrices, 2 by 2 matrices with determinant 1 with the real coefficient acts by Möbius transformation on the upper half complex, upper half space, and this preserve the metric. So this is exactly the group of isometry. So in that way, if you want H2 is what is called, if you took my courses last semester and the two courses we have last year, we spoke about symmetric space. So H2 is the symmetric space associated to this group SL2. So it's SL2 modulo the maximal compact subgroup, which is the orthogonal subgroup of SL2. So if for some of you I speak now above your head, if you never seen it, of course, it's you cannot follow. But soon I will come back to elemental stuff. I just want to mention this example, and this will give you an example of this implies that gamma is a lattice embedded as a lattice in the group SL2R, the group of 2x2 matrices. So we now have two examples of lattices in SL2R. I told you one example was SL2Z. I didn't prove it's a lattice, but I will prove it. And now I gave you another example, gamma, which is the fundamental group of the surface of genus 2. But you can, this is one example, this is a family of examples, because here every hyperbolic metric on this surface, and there are many, will give you another embedding, so will give you a different lattice inside SL2. All of these lattices will be algebraically the same group, which is defined by this law, but geometrically they will be different. You can imagine, of course, this is not the true picture. When we draw a surface like that, and we think of it as a subset in R3, that you cannot avoid positive curvature. But in reality, this is a negatively curved manifold. But we can think of another metric which will look like that. It will be much larger diameter. You can also and this will give you another embedding of the same gamma in SL2. So there are plenty of lattices in SL2 which are this group algebraic, which is a special. I say it because some of you who know a bit about rigidity realize that this is a special phenomenon of SL2. You cannot have something like that in SL3. In SL3, if you have two lattices which are abstractly the same, they must be conjugated. That's a rigidity that we have in higher dimension, and we don't have in SL2. Okay, so I wanted to mention this because now for those of you who took my last three courses, you see the motivation to study lattices. They are strongly related to locally symmetric spaces. So in the past three courses, we discussed the geometry of locally symmetric spaces, and now we want to understand about the algebraic properties of the fundamental group associated to locally symmetric spaces. So my main interest are lattices in Lie group, but we will also want to understand more lattices in totally different. Okay, so maybe now we'll have like 15-minute break, and after the break, I will start to describe elementary properties of lattices, like like compactness criterion, recurrence property, like topological property, dynamical property, and algebraic properties. And okay. Okay, recording. Okay. Recorded. So now we discuss some basic properties of lattices, and I mean, ask whatever you want to ask. I mean, we're not in a rush, anyone. So to solve a compactness criterion. So Here one. G and locally compact. And gamma G Gelander. So you want to know whether gamma is compact or not, co-compact or not. In particular, if it's not co-compact, you want to know what does it mean to go to infinity in G mod gamma. Let I in G to G mod gamma be the quotient. Then this is the criterion for a sequence for Gn in G, pi Gn goes to infinity. Is it clear what does it mean to go to infinity? In a locally compact space, to go to infinity means to eventually leave any compact set. So, i.e., eventually any compact set. So if and only if there are gamma n in gamma, but non-trivial, such that gamma n Gn, which is by definition Gn, gamma n Gn inverse, tends to 1 in G. That's the criterion. You go to infinity if and only if, yeah, it's similar to Mahler criterion. היי, דניאל הגיע. רגע, אולי זה איזשהו מצב. אפשר לצאת לחוץ? אולי תפנה לה. Okay. Okay, so this is a tune. So maybe I'll show you example. Okay, we'll see example. So intuitively, this must be true because I will soon give a proof, but let me just first explain why it should be true. So how do I think? I tend to think of G mod gamma as manifold. It's almost true to do that. And if it's not compact, then you can go to infinity. Suppose this is how I imagine G mod gamma. And like a manifold or like a, but it has finite volume, finite measure. And what does it mean to go to infinity? It means like that. So this will be pi Gn goes to infinity, and you see in pi, you must have shorter and shorter loops because some of the injectivity radius must go to 0. If you look at balls, there cannot be, if you fix any radius epsilon and look at ball of radius epsilon, it cannot be that the epsilon ball will be embedded. At some point, it must overlap itself, so there will be some loop. And this is how we describe loop. This is, gamma is the fundamental group. And what?
Which direction?
What?
I was trying to explain one direction.
Okay, one direction is easy. The fact that if Gn doesn't go to infinity, then this cannot happen. So I try to explain that if Gn go to infinity, then you must have a sequence of gamma n like that. So in a sense of, if you go to infinity in the quotient, then you must have shorter and shorter loops around this Gn, which will algebraically translate to say that the loop corresponds to gamma n, and this is the loop. Okay, this is just formally nonsense in a sense, also that it's not a mathematical proof, because in particular Gmod gamma is not a manifold, and what is a loop there? I mean, G could be totally disconnected, but still you can make it formal, and this is how this is the intuition works. So let's now try to make it formal, or let's try to present a formal proof. So actually you can make it.
Yeah, so but this expression means that gamma n is a loop around the fixed point by Gn, by conjugating by Gn, you move it to infinity.
Yeah.
Fixed.
It will be the same.
Yeah.
Gamma.
So let's give a formal proof. And this is a bit confusing, but let's try. So first direction, suppose I Gn do not go to infinity. Let's first suppose that. So up to moving to subsequence, I can suppose, so this implies up to taking subsequence that pi of Gn converge to pi of G0. Right, for some, this is local complex space. So that's now this implies that there are lifts such that okay, pi G n equals pi of Gn, so you can change Gn by an element in gamma such that Gn bar actually converge to G0. So we can suppose that our original sequence was Gn bar. We only say something about pi of it. So we start with that. So okay. So let W G be an identity neighborhood an ID neighborhood such that the discrete group gamma to the G0 G0 gamma G0 inverse intersect W trigger. So that's a discrete group. You can find such a and let V be a symmetric ID neighborhood so it means that V equals V inverse, which you understand what that means. Such that V cube is still inside W. Okay? V inverse means V inverse It's all the inverses of element which is inside the group. And I take it, so I have this is G. I fix some W which intersect trivially some lattice, the limit lattice. You have a sequence of lattices, and this, the red is this limit lattice, G gamma 0, and G gamma 0, gamma G0, gamma to the G0, intersect trivially W. And now I take a much smaller neighborhood, and I call it B. Okay. For sufficiently large n, we have that we need to do it in the right direction, but Gn bar which is the right direction. Let's say G0 inverse belongs to right, because G and bar converge to G0, so maybe I need to switch the order. I will do it like that. Okay, what does it mean? It means that gamma to the Gn gamma Gn inverse, I can write it as I want to write G0 gamma G0 inverse, and here something Vn. So Vn in this small set. So did I write it? This is the right way? Or not?
It's okay.
It's okay?
Mm.
Okay. So like it. So you see that now G gamma G0 gamma G inverse G0 gamma G0 inverse intersect W trivially, and therefore it also intersect V cube trivially, V cube trivially, which implies now that Gn gamma Gn inverse intersect V. And that's finished the proof of that direction. So it means that in particular, you cannot take a sequence of non-trivial. Yeah. This implies that there is no gamma n in this group, gamma to the Gn minus 1, such that gamma n to the Gn, there is no gamma n to the Gn, such that gamma n to the Gn converge, belongs to V. So it proves one dimension. Okay. So, okay, so this is the easier direction, but I mean, it's easier because it's straightforward. The other direction, in some sense, require a trick. It's a bit less straightforward, but it's also not very hard. So let's see the other direction. So here in this direction, we didn't use the fact that gamma is the lattice, only that it's 3. For the other direction, we will use that. So the other direction. Let W be an ID neighborhood. And I want to show that inside, for large N, you have an element in G in gamma to the Gn, which is non-trivial, and it's in W. Let I want to use V, so let M be the volume of the projection, the image of W inside the image of W inside G mod gamma. G mod gamma is a probability measure, so it's a finite measure. So this is a finite number. Okay. Now let K inside G be compact such that the volume of I of K.
Something, don't you want to ask it to be pre-compact?
Sorry?
Don't you want the identity neighbor to be pre-compact?
No. I mean, yeah, I mean, yeah, I don't need it. I only need it to, it's open and therefore the images in positive is there.
You want to conjugate it out, like.
No, now I want to conjugate in. And yeah, so in any neighborhood, I can take a sub-neighborhood. So now I take a W. So the strategy now is to show that for any W, so we have G, we have 1, and we fix any W, and I want to show that if I conjugate gamma enough, I will find an element inside W. I can go inside. So I take any identity neighborhood W, and I want to show, that's the next slide. We need to show, we will show that for large N, gamma to the Gn intersect W. Yes. So, yeah. So now I take K large enough such that the volume of this is bigger than 1 minus K. What is the picture should have in mind? You have this G mod gamma and W, and this is pi of W is something, the volume. I don't care so much. It has volume V. Now I delete it. And now I take K sufficiently large such that if I look at pi of K, then the volume of what's left here, the volume here is smaller than V, than M. So M was the volume of pi of W. So in a sense, if I manage to take W out there, it will must overlap itself. That's like the injectivity radius that I mentioned before. I'm trying to make formal the non-formal idea there. So let K, I can find such a compact set. Okay, so pi of K is compact. I see why all wanted me to take W to be pre-compact. It's helpful. So let V inside W be symmetric and pre-compact. Okay, but I want, okay, so actually, all suggested was true. I want to assume that, I can always assume that it's pre-compact. So let M.
Why can't you just do?
Yeah, I can.
V to V2?
I know, I just take, because I want M to be the volume of the pre-compact. So let, suppose W is big. Yeah, I can always do that because I take a smaller neighborhood. I just want to show that something intersects a neighborhood. If I take a smaller neighborhood, if it intersects a smaller neighborhood. Okay, thank you. So, yeah. So, since I of Gn is assumed to go to infinity, for large n, we have, I need to write it properly, we have that pi of W Gn intersect pi of K fitted. I can do that because this is equivalent, if you want, to the requirement that pi of Gn is not contained, pi of Gn is not contained in the compact set pi of W inverse K. Right? Equivalent to that. So that's a compact set, and this goes to infinity, so that's good. Okay, what does it mean? This means that the map, this implies that WGN, if I send it to WGN gamma, this map is this is a subset in G mod gamma. This map is not injected. Why it is not injective? Because the volume of the image is smaller than the volume of the origin. The volume of the origin is that like the volume of W, it's M. This the volume of this, the Haar measure of WGN is M. And here it sits inside the red part, which we assume it has volume less than it.
Means that the restriction of the quotient map to WGN is unobjective, right?
What?
Means the restriction of the quotient map pi to WGN.
Yeah, pi, yeah, that's what I mean. Pi, when I think of pi as a map from this subset.
So you should
Yeah.
the GN to the other side.
Okay, yeah, that's what I mean. Yes, pi, it means that
It needs to be,
pi
it needs to be back.
restricted to WGN is non-injective. Why? Because the origin has a volume M and the target has volume less than M. So the target is included in this set.
Should move the G. Otherwise, the measure will not be preserved. Of the W.
No.
If it has a lattice, it's unimodular.
Wait.
Well, okay.
Yes. And the measure here, I measured it inside G.
Yeah, no.
Okay. Yeah, thank you. So G is unimodular, so we don't care. By the way, you should stop. You should forget that there are non-unimodular groups because throughout this course, I will consider only unimodular group now because they are the only groups that admit lattices. But later we will talk about random groups, and then if you want, you can allow yourself to think about non-unimodular.
Can you repeat that now?
The last one.
You mean that the volume in G? It means the volume of WGN in G is bigger than
Okay, you want to be precise. So let's, before the proof, okay? Before starting the proof, we should say, we normalize the measure, the R measure. G such that the core volume of gamma is 1. If you want, such that you pick a fundamental domain and you normalize the R measure, you multiply it by the right scalar to make this volume. And now the map, now it will, if you consider the map from G to G mod gamma restricted to fundamental domain, it's measured to 0. Okay, and then you continue. Then you say, if I have a set in G, it has some measure, and I look at its image in G mod gamma, it has smaller measure, it means that the map restricted to that set cannot be included. Every set you can copy back to the fundamental domain, and if okay, so it means that this map is non-injective. The map I restricted to this set is non-injective. What does it mean? What does it mean that this map is non-injective? This implies that there are W1 and W2 inside W. Yeah, different. Such that and gamma in gamma, such that W1G equals W2G gamma. That's what it means to be non-injective. Which means that W2 inverse W1 equals it's Gn, right? Equal Gn gamma Gn inverse. And this is not the identity. So we found the desired element, okay, not in W, but in. We could assume in the beginning that W is pre-compact. Yeah, if you want.
It's just like V before.
Yeah, let's W. Okay, let's now start. Let me say what I should assume, right? Let's now hold the proof. I should start. Let U be an ID neighborhood and W a free compact symmetry subneighborhood such that W square is inside Q. Then the proof is coherent, and then you see that this element belongs to gamma to the GM, and it also belongs to W square. Yeah, and it's not very good. If you didn't like my proof, you can look at the Nathan. There is a different proof.
It's like it's even-
I think my proof is better. I mean, it's rare to beat Regonatan. It's but okay, in several places you can do it. Okay, I don't remember what is our good proof is here. This is an elementary theorem. I plan to give next time. I will give a non-elementary theorem, which was the theorem of Mostov about co-compactness of lattices in solvable groups, and for that we will surely beat Regonatan, which by far beaten Mostov. So Mostov original proof was extremely complicated. But when time goes on, the mathematical community, one thing that we manage is to take long, complicated proof and make them like nice and compact. So that's how all the classical results from 100 years ago are things you can tell in a few minutes. I mean, most of them. And today, when you want to say some new nice result, it's usually you have to spend a week to learn it. So yeah. So but with time, it's anyhow. This was never very complicated. So some example. So consider this group that we will soon prove that it's a lattice inside SL2R. And we claim that it's a lattice. Actually, we know a lot about this group. We know the fundamental domain, like Ziegler fundamental domain, and we know exactly to compute the volume, which is pi over 3, and so and so. And we know how to go to infinity. But let's see this in this theorem. So consider let gamma be the element 1, 1, 1, the unipotent element inside gamma. And let Gn be, if you want, this element and inverse. And you see that if you conjugate gamma by Gn, then you get the element 1, 1, 1 over n squared, which goes to 1. So this is the example, and if for those of you who are familiar with the upper half space and the unimodular surface, which is this I want to go to infinity, so I should go smaller, but you're probably familiar, some of you have seen this picture, which is coming from important in number theory or computation theory. So this is the fundamental group, the fundamental domain of SL2R modulo SL2Z, and somehow this pi of gamma n or pi of gn goes to infinity here, and the loop corresponding is the loop that comes from the action on the unipotent element, which is actually translation, maybe transformation. Again, I don't do it. I don't explain the details here. Example for those who are familiar with this stuff. In any way, this is a unipotent element. So let's give a definition that I like. Actually, I made this terminology, so it's not very well known. So, but a sequence gamma n inside G is called approximated unipotent if there are Gn inside G such that gamma n to the Gn goes to the identity. And there is the theorem that we just proved is the following theorem. With this terminology is the following theorem. A lattice gamma inside G is non-uniform, not so compact, if and only if it admits non-trivial
Gamma in gamma?
sorry?
Sequence gamma in gamma?
Gamma in G, but now it will be in gamma. So now it will be in gamma, approximated. Gamma n. Now it's inside. Non-trivial means that it's gamma, but not. So a lattice is non-uniform, non-compact, if and only if you can find a sequence of approximated unipotent. And as you see, if you take a single unipotent element, this unipotent element already give you approximated. But in general, we cannot find. So in SL2Z, I could take gamma n always to be the same element. And just change Gn. So if you have, so basically you see that if you have a Lie group, let's say a simple Lie group, and you have a lattice which admit a unipotent, then it cannot be uniform lattice, because any unipotent. By the way, you know what the definition of unipotent. A unipotent element is an element in a matrix group. It's an element that all its eigenvalue are 1. If you want over C, you can conjugate it to the Jordan form, and the Jordan form will be 1 on the diagonal and some 1 above. And so that's a unipotent element. But there is also a topological definition of a unipotent. In a semi-simple Lie group, an element is unipotent if and only if you can approximate 1 by conjugate. So maybe I'll mention it's relevant. Definition. But by the way, this is valid for also for totally disconnected. So definition, an element, a matrix, A unipotent if the characteristic polynomial A is, so A is now a matrix in M and it's x minus 1 and yeah, that's the characteristic. So all the eigenvalues are now that's the definition of unipotent. If G is a semi-simple, so remark remark the position. I'm not going to do it anyway, but it's good to know. This is not an exercise, but it's classical. You can find it in any classical book or semi-simple book. So if G is simple, semi-simple, let's say let's say linear. They're always linear up to center. If you take them, if you divide by the center, it's linear group. So it's like SLN. Then G inside G is unipotent if and only if the conjugacy class of G contains 1. So you can approximate 1 by conjugate of G. Then it's unipotent. Like we did here. And it's easy to show that if it's not unipotent, you cannot. And it's not very hard to show also that. So it's not a hard result if you know what to do. But so to be unipotent exactly means that you can approximate 1 inside the Lie group. Now I said what it means to be approximated unipotent, and a lattice is non-uniform if and only if it admits approximated unipotent.
Are there approximated unipotents that are not unipotents?
Yes, yeah, of course. Yeah, I mean,
In
Lie groups, you cannot do that. Yeah, in Lie group, of course, the sequence doesn't have to be constant here. You can take different unipotents, but you are right that yeah, I will give a related exercise soon, but you're right here. Okay. In fact, yeah. So let me give. Okay, first I should mention the classical theorem of Gelander and Margulis here, which was the conjecture of Selberg. Some theorem of Gelander.
You have an example where this remark is false, the group is not anything?
Sorry?
Maybe. We could take it and begin.
Okay. Semi-related question, maybe we'll save it for later, but I want to finish in 15 minutes and I still want to say a few more things about this theorem. So there is a beautiful theorem that I will not prove in this course. Of Gelander and Margulis, we say that let G be a semi-simple Lie group. If you want SLR, sufficiently interesting, and gamma a non-uniform lattice. Then gamma admits a non-trivial uniform. So that's partial answer to those questions. So if you have a non-uniform lattice in a semi-simple Lie group, it must have uniform. That's somehow the only possibility to go to infinity. It's only loops that can happen are corresponding to unity. Now, maybe I'll give you an exercise. An exercise, many results that were hard in the past, I mean, still hard for general lattices, are easier for arithmetic lattices. I didn't define what is an arithmetic lattice, but yeah, okay, let's do that. Okay, here is an exercise. It's a good exercise. So actually, the exercise, I will define arithmetic groups next week, but now I will say an exercise about arithmetic group without defining. So let G inside GLN R be a closed sub. Suppose GZ, which by definition is the intersection of G with GLNZ. GLNZ is the group of n by n matrices with integer coefficient and determinant 1. Should I write it? No. So suppose that this, what?
GLN or SLN?
GLN. GLNG is the group of, okay, determinant 1, so integer coefficient. And determinant, yes, so suppose that this is a lattice, non-uniform lattice in G, then GZ admits a non-trivial uniform. So in a sense, it's a proof of Krishnan-Margulis theorem for arithmetic group. I didn't say, well, this is an arithmetic group. GZ, when in that case, we will define arithmetic group soon. But if you have a non-uniform lattice which is like that, it comes from integer matrices, then you must admit unipotence. So this is somehow, this exercise explain the motivation of Selberg to make this conjecture. So at that time, people believed that every lattice is arithmetic, and actually Selberg conjecture it, and to some extent it's true, and I will talk about it next week. But at that time, accepting certain situation when they knew example like SL2, like I mentioned this hyperbolic manifold, but in general they thought that lattices always come from arithmetic structure, and it's almost true. And therefore, since this was obvious to Selberg, he conjectured this, and Krishnan-Margulis proved. Now let me give another.
So by the last theorem, this is an if and only if, right?
Sorry?
By the last theorem, this is an if and only if, right?
By
I mean, gamma is non-uniform if and only if it means not really.
yeah, but the if part is if you have the if part is. But it's not a hard exercise, really. It's I think it's yeah. And now let me give another exercise about totally disconnected group. Let G be an TDLC. So by the way, TDLC means totally disconnected locally coupled. That's a common domain node really. Like LCSC, it's locally complex second countable. Yeah, TTLC, you will hear it if you know the conferences. So let G be a TDLC group. And let gamma in G be a non-uniform lattice. Then gamma admits closure. Non-trivial then let's go to part A. Gamma being non-trivial closure. So closure means element of finite order. Should I give a hint or no? The hint is that it's related to something mentioned earlier today. It's a weak hint.
General.
General hint. And B is harder. Gamma means unbounded closure. So you can find elements of arbitrarily large finite order. Okay. This is an interesting.
What do you mean about like every
You can find
infinitely many versions?
no unbounded. Okay, that says two meanings. One is easier and one is harder. The easier is to show that for every n, you can find a finite subgroup in gamma of cardinality larger than n. And the harder is to show that for any n, you can find an element of finite order particular more than n. But actually, at the moment, I don't see the proof for this stronger statement, but it's in this note, so I trust the author, so it should be true. So, but the middle gamma it means unbounded closure, i.e. For let's say B1 for any n there is a finite subgroup of cardinality more than n, and B2 for any n there is, let's say, B1 and B2 an element of finite order bigger than n. So I see a proof for B1, and I think B2 should also be true, but I need to think. I mean, I probably knew. So this is another exercise, and now let's end. I plan to do much more than I managed today, but we'll do everything. We will not be in a rush.
Tsachik, just one question. Is this is the other direction, let's say for groups like OT, for example, is the other direction true?
Yes. Yes.
And can you state a general statement of when is this converse true?
Yeah. I mean, yeah, you have, yeah. Maybe at some point we should talk about totally disconnected group. And there is what is called a Searle's volume formula. Searle gives a volume formula for for lattices in locally compact group, in totally selected locally compact group acting on for instance, on the Cayley-Abel graph, and from that formula you see the torsion and the unboundedness of that. By the way, the reference for third volume formula is the paper that I wrote with Uri, Bader, Pierre Manuel Capras, and Shachar Moses about lattices in amenable group. I think the only way I know, only reference I know for third volume formula, and you can see the torsion there. So you can see exactly that if that the unbounded torsion comes when you have non-uniform lattices and it's bounded when it's uniform. And but you don't need a formula for this exercise. And let me give a consequence corollary for those of you who are familiar with the local field corollary, which is it's a very interesting corollary. It's let G be a periodic analytic group or a periodic algebraic group. So if you want, it's a periodic Lie group. It's like a e.g. SLN of QP. If you don't know what is QP, just ignore what I say. But it's good to know that such things exist, and so that's a totally disconnected locally compact group, which is also an algebraic group, and it has plenty of structure. There is Lie theory and blah blah blah, and it has many lattices. Then G, then all lattices in G are uniform. All lattices in G are uniform. All lattices in G are uniform. Why? So you don't have non-uniform lattices. And actually, this group admits plenty of lattices. We will prove that. We will prove that they have arithmetic group and arithmetic group.
Every periodic algebraic group.
If a periodic algebraic group, let's say, every semi-simple or perfect, then it can meet. But also uniform. And once you don't have characters, we will prove Borel-Chandler. So this group admits plenty of lattices that are all uniform. By the way, the same. It is not true if I change. You know, there are two types of local field, except there is R and C. That's the connected one, and the non-connected one. There are QP or finite extension of QP or function fields. Function fields are a local field of finite characteristics. And for function field, there are plenty of non-uniform lattices. But for periodic field, there are no. And the reason SLN or SLN QP and every closed subgroup, blah, blah, blah. It follows actually from SLN because you can embed any other group inside SLN, admits an open, compact, torsion-free subgroup. So you have an identity neighborhood which is not just open and compact and a subgroup, it's also torsion. And I can tell you exactly what it is. It's the first congruent sub. It's the group of all. You can take the group to be G1, which is the group. It's the stabilized. Yeah, it's a group of all G in SLN, such that G equals 1 mod of B. The first congruent sub. G, all the elements that sufficiently close to 1. This is a torsion-free sub. It's a torsion-free open subgroup. Once you find such a group, lattices cannot have torsion. You don't have torsion because so once you find a lattice may have torsion, but the torsion will be bounded. And okay, you see, this group must intersect trivially. Let me add another exercise because I can explain it in 3 minutes, but we only have 2, and it's good to have more exercise because it gives you things to work. If G has a torsion-free open subgroup, then lattices in G are uniform. Don't have non-uniformity. So this applies to periodic group. It does not apply to algebraic group of finite functions. Yes. Last question, and we want to finish early to have time for lunch because Midrasha is in 15:01. So yeah, but what's
No.
okay, so next week I will continue with this introduction. I will discuss, so this is like compactness argument, compactness criterion and application. Next week we will discuss things related to Poincaré current, like dynamical properties of lattices, and also other algebraic geometric properties. I will mention some open problems. Some of them may be hard and some of them may be accessible for students. And I will also explain what is an arithmetic group. And yeah, and the week after we will start with the